Hello, y'all, and welcome to lesson 113 of my DB chemistry curriculum. Today we're going over reactivity 3.2.13 and 14. This is an HL topic. So in 13, we're going to talk about how standard cell potential, E cell, can be calculated from standard electrode potentials. And if E cell is positive, it is a spontaneous reaction. Furthermore, in 14, we're going to talk about Gibbs free energy in relation to the standard cell potential. So to show the relationship between standard change in Gibbs energy and standard cell potential, we're going to be using a equation that is found in your data booklet. This will just be the standard Gibbs and cell equation. So with that said, let's just talk about calculating standard electrode potentials. Calculating standard, or sorry, not calculating standard, it's calculating with standard cell potentials. So how do we actually do this? And to do that, we're going to look at how composition of a battery affects voltage. Now, we have learned that voltage can be affected by a number of things. For example, we can use concentration to change the voltage, making the favorable equilibrium push towards a stronger voltage. But the easiest way to affect voltage is straight up with the composition of that battery. So as we do that, we should use an example. So let's do an example of the cell between copper and zinc. Now, oh, you know what? Instead of copper, let's change it to nickel. Nickel and zinc. So if we take nickel and we look at its reaction, nickel 2 plus 2 electrons, and we can find these values in the data booklet to form nickel, this reduction is going to have a voltage of negative 0.23 volts when compared against the standard electrode potential of the hydrogen cell. Um, and so we use SHE, the standard hydrogen electrode, as our comparison for all of these. We learned that in a previous unit. And then we can compare zinc 2 plus, its reduction potential. And we see that to become zinc, it has a voltage of minus 0.76 volts. So when we combine these, combine in voltaic cell, what we notice is zinc really doesn't want to reduce. In fact, it doesn't want to reduce more so than nickel. So zinc will instead oxidize. And when we write that, we can write Zn 2 plus, denoting the phase boundary, salt bridge, nickel 2 plus, nickel. And there we have our cell diagram. We can see here that zinc is oxidized. This happens at anode. And otherwise, nickel is reduced. And this is at cathode. Remember, anox, red cat. So to calculate the actual potential of the cell, we can say E cell, and this is a standard electrode potential because we're using standard values. Of the overall cell will just simply be E standard of the reduced species, and we're going to subtract that from E standard of the oxidized species. Whoops, that's spices. Species. There we go. Something of note before we move forward is that this is a subtraction because the reaction is oxidation, not reduction. What I'm talking about is our oxidized species, we're not using reduction like this reduction potential states. We're using oxidation, meaning we have to flip the value and turn that into a positive. So we do that using this negative right here. Plugging this into a reaction, we can find out that our cell is negative 0.23 minus a negative 0.76, and that's going to give us a voltage of positive 0.53 volts. Now, there's a couple things we know about this. First off, if we did this in a lab, we will likely get something very close to 0.53 volts if we're using 1 molar solutions of each. And if our cell is completed well and everything's working properly with little resistance in the wires, we'll get this voltage. Something else is because we're actually getting a voltage and this is a voltaic cell, we know that this is a spontaneous reaction. And that positive indicates that. Before we move further, I'm just going to take a brief pause. Using this equation is what it's required of you on the DP exam. So you need to be able to recognize and use this equation. Furthermore, you need to be able to recognize that this positive value indicates a spontaneous reaction. All right. With that clear, now that we are talking about spontaneous reactions, we are very likely going to jump right into Gibbs free energy. If we remember from previous, in the tail end of our enthalpy unit, when we talk about reactions, especially with Gibbs free energy, we use that to determine spontaneity. We also know that some reactions are reversible. Now, Gibbs doesn't necessarily state that, but a good example of that might be charging a phone battery. So we know we can reverse some spontaneous reactions. So basically, all we're doing is taking a non-spontaneous reaction and forcing it to move by doing one thing or another. But basically, we know that we can now use Gibbs to determine spontaneous versus non-spontaneous. We know that with Gibbs, if the change in Gibbs free energy is less than 0, that is spontaneous. And if the change in Gibbs free energy is greater than 0, that is not spontaneous. So now we know that we can likely relate this to E cell because our E cell value positive indicates a spontaneous reaction. So we need some equation to do that. Now, in addition to this equation needing to be able to be used for your DP exam, there is a second equation. This one is in your data booklet, and that is the equation delta G standard is equal to negative N F E cell. So you now have three delta G equations. One that uses the change in enthalpy and change in entropy, one that uses the Arrhenius factor, and one that uses the electrode cell potential of a voltaic cell. So depending on what situation we're using, talking about free energy, talking about spontaneity, you need to be able to recognize which of the three Gibbs free energy equations to use. Now, for this equation, we can define our terms. G is our Gibbs. This is generally given in joules mole inverse. N is specific to moles of electrons transferred, and that's of course in moles. F is a value from your data booklet, one that's more commonly used in physics, but this is Faraday's constant. That is a value of 9.65 times 10 to the fourth coulombs mole inverse. Lastly, we have our cell potential. and that's of course going to be in volts. So this is the equation that you need to recognize when to use, and then you need to learn how to use it. So let's use an example. We did nickel and I erased copper, feeling a little bad about that. Let's go back to copper. So let's look at a copper zinc electrode. Copper 2 plus zinc will react to form zinc 2 plus copper. I'm not really going to take time writing state symbols, but this is the oxidization of zinc in a copper solution. We can calculate that our E cell will be 1.10, positive 1.10 volts. That can be given to you. But how do we calculate the delta G? Well, delta G is going to be equal to negative NF E cell. And so we just get to plug in these values. Now, I notice that we have 2 electrons moving. And this is, again, a mole ratio. So for every 1 mole of copper ions, we're going to have 2 moles of electrons. So N is going to be equal to 2. Faraday's constant is constant at 9.65 times 10 to the fourth coulombs per mole. I'm not going to include units right here, right now, actually. And then lastly, our E cell is our 1.10. Now, one quick thing before we move forward is to notice that all these values are positive, but this is a spontaneous reaction. We know that because our E cell is positive. This is why we include the negative in this equation. It's going to shift our delta G to a negative value, therefore indicating spontaneity. So when we plug this whole thing in, we get, we get negative 212 kilojoules per mole. Now it'll come out to 200 or 2.12 times 10 to the 6 joules per mole, as Gibbs is in joules, but I shoved it over to 212 kilojoules just so that we can therefore not use scientific notation and instead just refer to it in kilojoules. Anyways, this is how you use Gibbs free energy. This is how you calculate standard cell potentials. Hopefully this helps, and have a great night.